My name is Luca Olmi, and I work at the Arcetri Astrophysical Observatory, which is part of the Italian National Institute for Astrophysics. And my background is mainly on the study of molecular clouds and star-forming regions, but I also have worked on the telescope design and instrumentation, and previously I have worked on projects such as the Large Millimeter Telescope and the Sardinia Radio Telescope. So today I will describe the concept of angular super-resolution and how this can be possibly implemented on a radio telescope. And I have been working on this project with a number of people, which are listed here, both at Arcetri and also at the Astronomical Observatory in Cagliari. Actually, the first thing I should mention is that INAF, and specifically the Sardinia Radio Telescope, is already involved in AtLAST 2, and specifically in the work package 3 regarding telescope technology demonstration. So there are a number of colleagues at the SRT which are already working on AtLAST. And so it's interesting that here today I will be discussing another useful project that might come out from the SRT, which may have application for AtLAST. So I will give a brief description of what is meant by super-resolution, and I will discuss a couple of methods to implement super-resolution on a telescope and specifically in radio telescopes. And finally, we'll describe very briefly some model and experimental results. So first off, what are the physical effects limiting the resolving power of a telescope? And of course, you already know about this, but it's probably good to remind that there are, of course, the optical aberrations, which can be minimized by a proper optical design. There is the atmospheric seeing, which is mainly a problem for optical infrared telescopes and can be minimized again with the use of adaptive optics, or otherwise just placing the telescope in space. But then there is the ultimate limit to angular resolution, which is always expected to be diffraction. And diffraction is considered to be a final ultimate limit, but as we will see, it is really not. So by super resolution, we mean, in fact, all those methods that can improve the angular resolving power, in this case of a telescope, beyond the classical diffraction limit, which for a single dish telescope is of the order of lambda over d, where d is, of course, the diameter of the primary reflector. So the concept is basically that if you modify properly the optics or the optical layout of your telescope, then you can possibly get a main beam which is smaller compared to the diffraction limited beam, which is, as I said, lambda over d. And in this way, you can improve your angular resolution, eventually with some side effects, such as the increase of the side lobes, as I have tried to show on this in this sketch. If you can do this, then it means that you improve your angular resolution, and therefore astronomical targets that were previously unresolved with your nominal beam, they will suddenly become resolved with your new improved angular resolution. So that's really a big improvement for a single dish telescope, if it can be done. So there are several ways that in principle it's possible to obtain angular super resolution on a telescope, and during the past 10-15 years there have been several proposals, and some of these proposed methods are, I would say, quite exotic sometimes. As a matter of fact, they have never gone beyond the basic physical principles. On the other hand, there are simplest methods to obtain angular super resolution, and probably the simplest method is the use of binary phase shift masks. Binary phase means that these are phase masks that can change the phase by 180 degrees, or otherwise leave the change the phase unchanged. And these masks are also known as Toraldo pupils. And the idea is that if you place one of these phase masks, one of these Toraldo pupils at the entrance pupil of the telescope, then in the focal plane, you can get a point spread function which has a narrower beam compared to the diffraction limit, and that's where you get your super resolution. And eventually, you also get higher side lobes. On the right-hand side here, I show an example of one of these Toraldo pupils, which basically are constructed by concentric coronae. These coronae either leave the phase of the wavefront unchanged, or they modify it by 180 degrees. They can be made by standard electric material, but they can also be constructed with, for example, metamaterials, which is another line of research that we are pursuing. So how do you interface the Toraldo pupils on a telescope? Well, there are basically two methods. The first one basically follow what I said in the previous slide. You basically have to, ideally, you place this face mask at the entrance pupil of the telescope. So for a big radio telescope, that means that you have to place this mask at the aperture plane of the telescope, and that can be quite cumbersome, to say the least. Or otherwise, you can place the face masks at an exit pupil of the telescope. That's much easier in principle. Then it has some optical additional problems, but basically then can be done, for example, by using a two lens or two mirrors collimator, where you can place the phase mask in between the two lenses at the exit pupil of the telescope. So let's see a brief description of these two methods. I'll start with the second one. This is a grasp model for the Medicina telescope. And at the focal, near the focal plane, you can see a two-lens collimator with the Toraldo pupil in between. This is a design that we have been testing in K-band at 20 gigahertz. And the electromagnetic simulation actually tell us that the model works as it is expected. And so you can see that when you utilize this super resolution optical module, you get a main beam, which is narrower than the lambda over the diffraction limit. But at the same time, you also get this increased side lobe. And in this case, the two beams are normalized, but besides the higher side lobes, you also get a decrease in efficiency when you use this super resolution optical module. This kind of method has a number of problems and disadvantages, which I can describe in detail if there are questions in the end. But for the moment, I will simply go to describe the other method, which involves the use of active surface. This is interesting, particularly for our National Institute for Astrophysics, because INAF operates 3 radio telescopes in Italy, 2 32 meters dishes, one in Medicina near Bologna and the other one in Noto in Sicily. And then a third telescope in Sardinia, the Sardinia Radio Telescope, with a 64-meter primary reflector. Now, they all have operational active surfaces, with the exception of the Medicina telescope, where the active surface is is currently being constructed. So the use of active surface for INAF is particularly important. What is the concept behind the use of the active surface to simulate Turaldo pupils? That, as I said before, in principle, you would like to place the Turaldo pupils on the aperture plane of the telescope. Now, you can have a phase mask with a 64-meter diameter. So basically what you do, you use instead the active surface of the telescope to simulate the operation of this phase mask. And the phase shifts introduced on the wavefront are implemented in reflection rather than in transmission, as it is shown schematically in this slide, where basically, as you can see, when you shift a panel from its nominal position, you are introducing an excess optical path, which is equivalent to a phase shift. And therefore, by changing, by moving the appropriate actuators and the correct panels on the active surface, you can indeed simulate a corona, a single corona, for example, that is introducing a 180 degrees phase shift. So this is the concept behind implementing Turaldo pupils using active surface. There are, of course, some problems also with this method, because ideally you would like to have an active surface where each panel can be moved independently from all the other adjacent panels. Now, you cannot do this with normally the real active surface of telescope, because, for example, on the SRT, each actuator is shared by 4 panels. And so every time you move an actuator, you're not moving a single panel, you're actually moving 4 of them. And by doing this, you are introducing not only a translation of the panel, but you're also making it to rotate. And unfortunately, this introduces some unwanted phase aberrations. So the question is whether these unwanted aberrations are enough to basically vanish the super resolution effect. And the answer is both yes and no. It is yes in the case of the Noto active surface, but it works for the SRT. The reason is shown here. On the left, you can see the representation of the Noto surface with these little white discs represent the position of the actuators, and you can see the individual panels. The yellow area represents the corona of a 3-corona Turaldo pupil, and this corona is the one that is supposed to introduce the 180 degrees phase shift. On the right-hand side, you can see the same geometry applied to the Sardinia Radio Telescope. Now, even by eye, you can see that on the right-hand side, the yellow area is covering many more actuators and panels. That is because basically the spatial resolution of the active surface on the SRT is much better than it is on Noto. And as a matter of fact, our electromagnetic simulations show in the past that this method would work on the SRT, but it cannot work for the Noto surface. And it is interesting actually to see where the AtLAST active surface stands here, because basically with its over 100 panels, is basically is in between the Noto and the SRT. And so whether this method could in principle be applied to AtLAST is really something that should be carefully studied. So we wanted to test this method. So we knew it wouldn't work with the Noto active surface. So we went directly to the SRT and we implemented several geometries of these Toraldo pupils using the active surface of the primary reflector. And here is an example of a sort of a three corona Toraldo pupil. So the yellow area represents the area where these panels were moved with the appropriate shift. And then we perform some cross scans of a calibrator, in this case 3C84. And here you can see the results of some of these cross scans, where in blue, I hope you can see it, the dotted blue line represents the nominal beam of the telescope with no activation of the active surface. And the black solid line represent the beam obtained with the super resolution mode. And as you can see, we get indeed a beam in super resolution mode, which is narrower than the nominal beam. And it's narrower by a factor of about 1.6, 1.7, maybe even 1.8. The two panels represent two different geometries for these different corona, and they both works. The one shown here, we also had some that did not work, and eventually I can also explain why this happens. And the red dashed line represent the grasp simulations. So the method works. We also did some maps of the calibrator. From the left side, you can see the nominal beam obtained with mapping 3C84. You can clearly see a coma lobe that was present at the time of the observations, and right now the staff at the SRT is working to remove it. And then the two panels on the right-hand side is the map of 3C84 obtained with in the super resolving mode. And maybe you can see better if I use the zoom image. The white circle represents the full width of maximum of the nominal beam, the one with the comma, and the red circle represents the full width and maximum in super resolution mode. And so you can clearly see that the main beam is indeed narrower. This is the first demonstration ever of super resolution obtained with a telescope. In these maps, you can also clearly see the higher side lobes. Now, of course, you may wonder, well, with this side lobe so high, you cannot do any real astronomy. That's not the case. We also try to verify that, and we'll do more tests in the upcoming months. But here is an example. We also mapped a real astronomical source, the Crab Nebula. And you can see on the top row, there are two maps. The map on the left is obtained with the standard mode with the nominal beam, no super resolution. And on the right-hand side, you can see the map obtained in super resolution mode. Of course, it doesn't show in this map any angular super resolution, apparently. And that's simply because, of course, you do have those high side lobes that basically give this map as a final result. But if we apply a two-dimensional deconvolution using the beam that I showed before, you get the map on the bottom left corner. That's the deconvolved map, and then you start to see something interesting. You can see that now you have to remember that the Crab Nebula at these wavelengths doesn't really have a lot of features, of interesting features. So you can basically see that we see a little more details, morphological details, which are comparable, I would say, with the VLA map, which is shown on the bottom right corner,
Luca,
which was obtained.
Sorry to interrupt. Maybe we can
Yes.
wrap up because otherwise we don't have time for questions.
Sure. Then this was basically my last slide. And so next is just the conclusion. So super resolution has been demonstrated. The implementation with an active surface definitely preferable for a number of reasons. You have to pay the higher resolution with a loss of efficiency and higher side lobes, but this will not prevent astronomical observations. We are planning to make more tests at the SRT, and the big advantage of this super resolution method is that it can really enhance the mapping capabilities of a single dish telescopes. And of course, I was thinking also of AtLAST as a possibility. And that's all.
Thank you.